Good morning, students. Today in this session, we'll discuss about the IIR filter design, digital filter, IIR filter design. Digital filter, where we are going to discuss about the IIR filter design, that is infinite impulse response. The impulse response coefficients are infinite. So the infinite impulse response filter, it is a why the infinite impulse response? Because of the feedback. Because of feedback, it produces infinite number of impulse coefficients. So infinite IIR filter feedback system is also called a recursive system. Recursive system. So recursive means feedback. So because of this feedback, which produces infinite impulse response coefficients. In general, the transformation representation for this nth order IIR filter, for nth order IIR filter can be represented as h of z is equal to, you know that y of z by x of z. It can be represented as, so instead of time domain, I am representing in the frequency domain directly. So z domain, so b0 plus b1 z minus 1 plus b2 z minus 2 plus up to bm z minus m. So everyone should know that the transfer function h of z is a rational function. So this is a mantra for the transfer function. Y of z by x of z can be represented in z domain. So the denominator terms are 1 plus a1 z minus 1 plus a2 z minus 2 plus an z power minus n. So normally m, so you can represent the numerator polynomial coefficients divided by the denominator polynomial coefficients. So the y of z by x of z can be represented as numerator polynomial coefficients and the denominator polynomial coefficients. So the numerator polynomial coefficients are called zeros of the system and the denominator polynomial coefficients are called poles of the system. Poles of the system. Poles of the system. So any difference equation can be converted in the z domain. It is a frequency domain. So which is a rational function, numerator polynomial, denominator polynomial coefficient. The numerator polynomials are zeros and denominator polynomials are called poles of the system. Okay. So if you consider, so you can write now the h of z is equal to the summation of k equal to 0 to m bk into z minus k divided by the summation 1 plus the summation of k equal to 1 to n ak into z power minus k, where the ak and bk are coefficients of feedback and feed forward coefficients. So the feedback ak is a feedback coefficients. Okay, feedback coefficients and AK BK are the feed forward coefficients. Feed forward coefficients. So because this feedback only, it is called, say, rational number. It's a rational function. It's called IIR filter design. There are different types of structures to implement this IIR filters systems. There are different types of structures to implement this IIR for realizing hardware realizing IIR systems. For realizing IIR systems. Okay, the first one, there is a direct form 1. One is a direct form 1 structure, and the second one is the direct form 2 structure, and cascade form structure, and parallel form structure, and the lattice structures. So this one we can, so we'll in this session we'll discuss about the direct form 1 and direct form 2 structure implementation. So directly we can realize this system with these coefficients b0, b1, b2, b3. So x of z is equal to, that is a b0 into x of z. So we'll see how to realize the system in direct form 1 structure, okay, and direct form 2 structure. The direct form 1 structure, implementation. So if you see here, this is a all zero system, this is a all zero system, this is all pole system, this is a all zero system. The numerator polynomials are called all zero system and all pole system. So remember that the zero system coefficients are bk. The poles, all poles, here I denoted ak. So different books, different notations are used. Sometimes the ak will be here, the bk will be here. So you don't bother about the parameters, but the numerator polynomial coefficients are called all zero system. The denominator polynomial coefficients are all pole system. That is the concept. Okay, now we can implement the direct form 1 structure. In the direct form 1 structure, so x of z, so here direct form 1 structure we'll discuss. So this is x of z. So x of n is, that is x of n is given. So it is delayed by, so first two coefficients, the numerator coefficients is b0. So this is the coefficients b0. So the coefficient b0 into, see here, b0. So that is equal to y of z by x of z. Okay, so it is equal to h of z. Okay, it is equal to this one. So this, otherwise you can remember this also. So x of b0 into x of z plus b1 into z minus 1, delayed by 1 unit sample. So even if you see here, the what are the processings are involved here. This is a delayed by 1 unit, delayed by 2 unit. Okay, so unit delay element and the scaling factor, multiplication factor b1 and the adder b0. So the three important components are multiplier and adder and delay element. The delay element, unit delay. The unit delay is denoted by z inverse, multiplier, scaling factor and the adder elements. So these three elements are plays a vital role to realize the system, hardware realization of the IIR system. So when you go for implementation, so the how many the multipliers, adders and delay elements are memory locations. This is a memory. So delay elements is called memory and location, memory element. Okay, registers. How many memory locations are required to implement this system? How many multipliers? How many adders? So this is a hardware realization. In hardware realization, okay, when you go for hardware realization, how many multipliers are required? How many adders are required? Okay, how many delay elements are required? So the delay elements, hardware utilization, the delay elements, how efficiently we can use the delay elements in different form of structures, that form 1 and that form 2. We'll discuss about how many delay elements are required for that 1, that 2. That we'll see in this session. So B naught. So delayed by, so what is the meaning of 1 unit delay? Z minus 1. Then it should be given to, again B naught. This is, what is the meaning of this one? X of Z into Z minus 1. Okay, B naught into X of Z, B naught into X of Z. So B naught into X of Z. Then here this one is B1 into Z inverse into X of, what is the output of this one? Z inverse into X of Z. Z inverse into X of Z. Okay, then this both will be added. Adder element here. This is adder. Okay, then the next again B2 delayed by 1 unit of unit delay element Z minus 1. So if you want to get 2 delay element, 2 delay Z minus 2, so the first one will give Z minus 1, the other unit delay element will give Z minus 1. So now the output will be Z minus 2. Simply should not draw Z minus 2 like this. This is wrong representation. Only unit delay. So Z minus 2 can be represented as unit delay by 1. Again, which will be delayed by another unit delay element 1. So it will be Z minus 2. Okay. So this is a wrong method to represent the unit delay element Z minus 2. So now Z minus 2. So it indicates, so B2, what is the coefficient? See here. So one example B2 into Z minus 2. So B2, B2 coefficient and Z minus 1 and Z minus 1 will get Z minus 2 into X of Z. Okay, again which will be added. So adders. So this is the multiplier scaling factors and these are the adders. These are the unit delay element. So which will go to, so Bm, what are the coefficients of the numerator polynomial coefficient 0 system? So A Bm into Z minus M. So Bm into Z minus M. So you can write, so Bm into, so Bm minus 1, first we can take Bm minus 1 also. So one more I will draw here. So delay element Z minus 1, so which will be Bm into Z power minus M to X of Z. This Bm minus 1. Okay, sorry, here Bm minus 1. Bm minus 1. Bm minus 1 Z power M minus 1 minus M minus 1 X of Z. So this one again. So last one is Z inverse unit delay element. So last element is Bm. So I'm representing 2 at the beginning and the last one Bm into Z power minus M into X of Z. Okay. So this is the how to represent the all zero system, or you can say here the system. So all zero system is called, so this is a FIR system. The all pole system is called IIR system. This is a FIR system. This is your IIR system. So this FIR system represented. So this is your all zero system. Okay, FIR system, or you can call all zero system. All zero system. Okay, that is FIR system. Okay, now we can represent the all pole system. So the transfer function h of z, because we are going to represent the transfer function h of z. Okay, so y of z. So now the all pole system can be represented as, so it's a feedback system. AK coefficients are called B feedback system. So the output of this will be y of n. Okay, that is y of z. So in difference equations will be y of n, you can say. Now, so here the delay element represented by unit delay Z inverse. So what are the coefficients here? A minus A1, correct? What are the coefficients? 1 minus of minus. Okay, actually it should be written as 1 minus of minus A1 Z inverse minus A2 Z minus 2, like that it will go. Minus an z minus n. So minus a1 plus. Okay, this is a from the general difference equation. This is a general difference equation. From that you can write minus feedback system. So this is a all pole system. Okay, I can represent this as all pole system. All pole system z minus 1. Now 1, this is a 1. Okay, always it is 1. So 1 minus a1. Minus a1. So this is another all pole system. I put minus a1. So minus a1 z inverse unit delay element into y of z. This is a feedback system. So what is the meaning of this one? Y of n, if you given in terms of, you can write the delay element y of in the difference equation, you can represent like this. Here you can represent x of n. No? So what is the output of this one? X of n minus 1. So the difference equation only we are representing in the z transformation, z domain. Okay. So 1 minus, this is 1. Okay, 1, because the coefficient starts with it. So 1 plus. Okay, 1 plus. So next one, you delayed by unit delay element z minus 1. So the scaling now, the adder. So what is the coefficient here? So the coefficients minus a to z inverse y of z. Okay. So 1 minus a1 z inverse y of z plus minus a to z minus y of z. So which goes, so continue this one. Again z inverse. So what is the coefficient? A minus a n minus 1 minus a n minus 1 z power minus n minus 1 into x of y of z. Okay, so minus an z power minus of n minus 1 into y of z. So again you can draw this one, you can extend z inverse. So finally minus a n z minus n into y of z. So this rational function all pole system can be represented by this is all pole system. So this rational function, this one h of z, b0 plus b1, b0 plus b1 z inverse plus b2 z minus 2 bm, these feed forward coefficients and the feedback coefficients, all zeros and all poles with respect to the feed forward and feedback coefficients can be implemented, can be realized in that form 1 structure. So this is that form 1 structure. So if you see here, so how many, this is the all pole system. Okay, so this is your all pole system. The denominator term is all pole system, or you can say IIR system. IIR system, this is FM. It's the all zero system and all pole representation. Okay, so if you see in that form one structure, the M, how many multipliers are required? M plus N plus 1 multipliers are required, and M plus N adders are required. What is M and N? So M is the zeros and N is the poles. The poles only order of the filter. N is equal to poles, order of the filter. Order of the filter. So normally M should be less than N. Okay, M should be less than N. So this is the order of the filter. So to realize this system, it requires M in direct form one realization, M plus N plus 1 poles, M plus N plus 1 multipliers, and M plus N adders, and the delay elements, M plus N memory locations. M plus N memory locations. Memory locations are required. So how many memory locations? See, 1, 2. So this much delay, M delay elements, here N delay elements. So M plus N delay elements are memory location. Delay elements only. Okay, the delay elements and memory locations are needed to realize the system. Okay, now the same structure can be, so this one, okay, normally we can say this system, okay, that from one structure, the number of delays is not equal to the number of order of the system. So it's called non-canonic structure. Non-canonic structure. Canonic means number of delays is equal to the order of the filter. The number of delay elements is equal to the order of the filter. What is the order? N. If the memory locations, number of delay elements, the required number of delay elements or memory location which is equal to N means it is called canonic structure. Canonic structure. Canonic structure. So in this diagram, one structure is not equal to the order because M plus N memory locations. M plus N memory location. So in that case, it is a non-canonic structure. Non-canonic structure. Okay. Now we can represent this structure. We can rearrange this direct form 1 structure, which is called direct form 2 structure. Direct form 2 structure. So how do you represent the direct form 2 structure? So in this structure, okay, we'll keep this as such, the all zero system. Just you place this all pole system to the right hand side. Just you interchange the position. All pole in front of the all zero system. Okay, how do you redraw the structure, a rearrangement of the structure? See, the zeros, we don't change the zeros structure as such. We can keep, so then from two structures, so I'll draw it here. The all zero system. So all zero system. All zero system, the delay element Z inverse. So it is all zero system representation Z inverse So this is B naught. So what is the all zero system coefficients? B naught, B1. Same. I am only rearranging the system. B naught, okay, and this is B1. So this is Bm minus n minus 1, Z1 minus m minus 1. It should be continued. That inverse delayed by unit sample. So minus Bm. So same structure. See that the same B naught, B1, B2, and B3. B1, B2, Bm minus 1 is Z bar minus 1. Then the last one is Bm. Okay, the feed forward coefficients, FAR coefficients, all zero coefficients. All zero coefficients. Okay, now you place this all pole systems in front of the all zero system. Okay, we are going to place this one, all pole system, in front of the all zero systems. So remember that. So how the structure adders and the left hand side, delay elements are the center. Delay elements are the center ones in position. Z inverse. So Z unit by delay element. What are the coefficients? See what are the coefficients here? So this one we are placing. So first start with the 1. Start with the 1, 1. Then to start with the minus A1 into Z inverse into X sub Z. Then the coefficients are minus A n minus 1. So this will be minus A n minus Bm and minus A. Okay. So now, so this is X of n. So the just you are replacing these all pole systems in front of the all zero systems. So by rearrangements, how the delay elements are reduced. That is the concept for this structure. We are going to reduce the number of delay elements by using this structure. So here also we can do. So, okay, X of Z, X of Z, this is Y of Z. So this is we are going to connect these two. So in this from this structure, so in this structure we are replacing, we are doing rearrangements by placing this all pole systems in front of the all zero system. Okay, so B not coefficient. So remember that A and all, B and all feed forward. So this now this system is as such FAR system, all zero system. Okay, this now you are doing the rearrangements by placing all pole systems, that is IIR systems, in front of the FAR systems. Now you can this structure. Okay, now this structure, if you see this structure, you can rearrange into a single system. So this adder, so these two delay elements, okay, these two delay elements can be combined together. Okay, this so one single delay element Z inverse. Okay, Z inverse single delay element. So this from this the output will be here minus B1, that is a B1. This is your B0. So the left hand side the coefficients are minus A1. So now you can combine these two systems. By combining this structure, you need only one delay element. Combining these two delay elements together will get, so this is x of z or x of n, you can say. So now the output y of z is y of z. Okay, so these two delay elements are combined together. Okay, the structure, again these two will be combined together. Again these two will be combined together. So combined together, so another delay element z minus 1, because z minus 2, this is z minus 2. Okay, z minus 1. So now this will be, so the coefficients are, okay, b, so like that we will go. So b0, b1, this is b2, we'll take one more. One more. So delay element and add us. So A0, so this is minus A2, so it will continue. So delayed by unit delay element. Okay, so here AB, okay, so here, so minus AN, this is BM, BM coefficients, BN minus 1 minus AN minus 1, BM minus 1. Okay, it will be again. See the last coefficients Z inverse. So this is Z inverse. Okay, this is Z inverse. So coefficients for feed forward and the feedback coefficients. So BM coefficients. This is minus AN coefficients. Minus AN coefficients. BM coefficients. So this structure is called direct form 2 structure. Direct form 2 structure. So in this, so we are rearrangement of all pole and all zero system, we can reduce the number of delay elements to realize the system. Okay, so now the requirement of adders and multipliers and delay elements are for implementation of this system m plus the number of multipliers and adders for this system to implement in hardware. M plus n, okay, minus 1, m plus n plus 1 multipliers, m plus n adders, and the maximum of m comma n. Okay, maximum of m comma n memory locations. Memory locations. So this form is called canonic form. Canonic form structure. So if m is normally the condition is m should be less than n. Okay. So canonic form. So number of poles, poles is equal to order of the system. So in the canonic form structure. In the canonic form structure, because what do you mean by canonic form structure? The number of delays is equal to the order of the system. The number of delays, the number of delay elements, delay units, the number of delay elements or memory allocations or delay elements is equal to the order of the system. Order of the system. Okay, this is a simple realization of the with the system function, with the system transfer function h of z, direct implementation of h of z, okay, in that form 1 structure and that form 2 structure. So that form 2 structure, so remember that, so you know how the that form 2 structure we have arrived by rearrangement of the all pole and all zero system. But for a given rational function, the numerator and denominator polynomial coefficients can be represented in terms of a1 and b1 coefficients with the direct form 2 structure. So you can follow instead of that one. If you are not specifying, you can draw the for the given transfer function. You draw the direct form 2 structure. Okay, in which the number of delay elements are reduced. So remember that a1, a2, an are feed backward coefficients, and b0, b1, b2, and bm are the feed forward coefficients. So this is one. Okay. So we'll take some examples to realize the given system. So we do one problem. Otherwise, I will take the. Okay, we'll take one example. Okay, from the consider this equation. Y of, for example, if the problem is given, y of z plus 1 by 4 z inverse y of z, plus sometimes the difference equation can be given. You have to take z transform, z minus 2 into y of z, which is equal to x of z plus z inverse x of z. So this is a given, this is a problem as given. Simplify this equation y of z. So 1 plus 1 by 4 z inverse plus 1 by 8 z minus 2, which is equal to x of z 1 plus z inverse. So you know that the transfer function y of z by x of z, which is equal to 1 plus z inverse by 1 plus 1 by 4 z minus 1 plus 1 by 8 z minus 2. So we know that the h of z is equal to is a rational function which is denoted by the numerator polynomial coefficients divided by the denominator polynomial coefficients. The numerator polynomial coefficients are called the all zeros of the system, and all zeros, and denominator polynomial coefficients are the all pole system. So how to realize this in terms of direct form 1 structure. So in the direct form 1 structure, in the direct form 1 structure, one, first we'll discuss with dat form 1 and dat form 2. So in the dat form 1 structure, how do you draw the dat form 1 structure? So dat form 2 structure, that both will discuss now. So in the dat form 1 structure, first one will be, remember that dat form 1 means first all 0, then followed by all pole. So this is all pole 0, all pole is 1 plus z inverse. So x of z, 1 delay element. So this is m, this is m, okay, this is n is equal to 1, n is equal to 2. m is equal to 1 and n is equal to 2. So x of z delayed by 1 unit z inverse, you will get z inverse into x of z. Okay, so it will be given z inverse into this is 1, so this is your 1 plus z inverse. So this is a direct form 1 structure as such we have drawn. Then the all second half will be all pole system. So in that this is a y of z. So it will be, what are the coefficients here? So z inverse unit delay, this is y of z. So I told you, you write 1 minus of minus 1 by 4 z inverse minus 1 by 8 z minus 2. So z inverse, so what is the coefficients? So first 1 by 4 minus 1 by 4 z inverse, another delay element z minus 1, so we'll get that is z minus 2. So minus 1 by 8 z minus 2. So this is a direct form 1 structure. This is a direct form 1 structure y of z. So now we'll discuss how to realize the system in direct form 2 structure. So how many delay elements are required here? So 1 delay element, 2 delay element, this is a 3 delay element. 3 delay elements. So m plus n, what is m is equal to 1, n is equal to 2. So m plus n delay elements, 1 plus 2, so is equal to 1 plus 2. So 3 delay elements. So 3 delay elements are required. 3 delay elements required to implement the structure. The same will realize in direct form 2 structure. Direct form 2 structure. Direct form 2 structure. Direct form 2 structure. So in this, replace all pole system first. So combine these 2 delay elements, directly we can draw. So it requires in direct form 2 structure, we require only n delay elements. What are the n delay elements? N is equal to 2 delay elements. Only we need 2 delay elements. So z inverse z minus 1. Okay. So left hand side, what are the coefficients will be? All pole first. What are the poles? The poles are 1 minus, these are the poles. Minus 1 by 4 minus 1 by 8. So these are the pole minus 1 by 4 z inverse. The other pole is minus 1 by 8 z inverse. Sorry, 2 delay element z minus 2. Delayed by 2. So this is all pole system. All pole system. X of z. This is y of z. So here, what are the all zeros? What are the zeros? Z inverse 1. 1 plus. So the remainder here 1 plus z inverse. So 1 and z inverse. So this is 1. Y of z. Okay, so this is the direct form 2. So now here the delay elements requirement is reduced. So n is equal to 2. In the previous case, direct form 1, 3 delay elements are required. In this case, in direct form 2 structure, the number of delay elements requirement is n is equal to 2. So this is a canonical structure, canonic form. Canonic form means what? The number of delay elements is equal to poles, number of poles of the system. Number of poles of the system. Poles of the system. That means n is equal to, you can say the number of poles of the system, you can say is the order of the system. Order of the system also. Similarly, you can take another example. You can practice h of z is equal to 2z cube minus 4z squared plus 11z minus 8 divided by z minus 8 into z squared minus z plus 3. So you have to simplify this transfer function. So you can simplify, take z cube outside. Z cube outside you can take. So you can take 2 minus 4z inverse, 4z inverse plus 11 z minus 2. So z minus 2, so z minus 8 z minus 3 divided by, so you can take z, multiply these two. Okay, so z cube minus z squared, z cube minus z squared plus 3z minus 8z squared and plus 8z minus 24. Simplify this. So the denominator term will be z cube, will take z cube outside. So z cube minus minus 8z squared uh, minus 9z squared, 11 is 8 z plus 11. So 11 is z minus 9 z squared minus 24 denominator term. So numerator terms are, so z cube, so let it be z cube. So you can take again, so we'll write as such z cube into 2 minus 4 z inverse plus 11 z minus 2 plus minus 8 z minus 3. So now again you can simplify the denominator term. Z cube you take it outside. So 1 minus 9 z inverse and plus 11 z minus 2 and minus 24 z minus 3. So the numerator terms are z power 3, 2 minus 4 z inverse plus 11 z minus 2 minus 8 z minus 3. So these two terms will be cancelled. Can write y of z by x of z, which is equal to 2 minus 4 z inverse plus 11 z minus 2 minus 8 z minus 3 divided by 1, okay, minus of 1 minus 9 z inverse plus 11 z minus 2 minus 24 z minus 3. So what these are the, so you can represent in terms of all zeros and all poles of the system, because the numerator polynomials are all zeros of the system and the denominator polynomial coefficients are poles of the system. So now m is equal to 3. This is m. Okay, m is equal to 3 and n is equal to 3. So now what is the order of the system? The number of poles. This is number of poles. The number of poles is called order of the system. Order of the system. Order of the system. And to realize the system in that form 2, we need the number of poles. That is a n is equal to 3. So the delay elements are the actually maximum of m comma n. If m is equal to n, here both are same, so order of the system. So the delay elements equal to the number of delay elements requirement is delay elements or memory locations or number of delay elements are 3. 3 memory elements are required. Now you can realize the system either in that form 1 structure, or you can realize in that form 2 structure. So once if you know the concept of diet form 1, how it is rearranged into diet form 2, directly you can implement by using diet form 2. It's okay. There's a canonic structure. Canonic structure. So how you can realize the system? So how many elements or delay elements are required here? 3 delay elements are required. So the 3 delay elements, you draw the 3 delay elements. One, second delay element, Z inverse, Z inverse. So I'm not drawing that from 1 again rearrangement that. So once you know the concept in that form 2, the delay elements are reduced. So how many delay elements are required for that form 2 realization? 3 delay elements are required. So how do you represent the 3 delay elements? By 1 only. So this is delayed by 1. Again this is delayed by 2. The third one is delayed by 3. So what are the coefficients? So left hand side always poles, right hand side zeros. So poles, what are the poles here? So what are the poles? 9. So this is 9. So you write 1 minus of, you write 9 z inverse minus 11 z minus 2 plus 24 z minus 3, because the formula is 1 minus. So what are the coefficients? 9 minus 11, 24. For 9 for the first delay element, 9 for the first delay element, and the second delay element is coefficient is minus 11 and plus 24. So this is minus 11, this is plus 24. Okay, so this is z minus 9, z inverse, this is z minus 2, this is z minus 3. Okay, so you can add, so this will be add. So this is x of z. X of z. So now this y of z. This is y of z. So what are the coefficients? Zeros. So what are the zeros here? So the zeros are, what are the numerator polynomial coefficients? Zeros are 2 minus 4, 11 minus 8. So 2, this is 2 minus 4, 11 minus 8. 2, this is 2 minus 4, 11. Last coefficient is minus 8. Minus 8. Minus 8. So 2 minus 4 into z inverse, 11 z minus 2 and 8 z minus 3. So this is y of terms. So that's a direct form realization. So with these two examples you can understand clearly. I hope that you clearly understood the direct form 1 structure and direct form 2 structure implementations of IIR filter. Okay. So the number of delay elements is 1, 2, 3. The coefficients. Remember that in that form 2, left hand side coefficients are poles, right hand side coefficients are zeros. Okay. So you can practice, you can take more problems from the John Procky's or opening Arnav take more problems and practice how to realize the given transfer function in direct form 1 structure and direct form 2 structure. Okay, so direct form IIR filter realization. So if you see the two problems, okay, hope you understood this session. So next session we'll discuss about the IIR digital filter design by using different techniques, bilinear transformation and impulse invariant method, and how to design a digital filters from the unlock filters, the uh, commonly used unlock famous transformations, the common used unlock filters, Butterworth and Chebyshev filters, how the poles are located, we'll discuss in detail. Thank you.